In earlier lectures, we had started with some plots or graphs and asked ourselves a question: what causes the system to respond to signals in a certain way? We defined time constants for first order systems and saw how the speed of the response depends on the time constants. We also saw how in certain cases of second order systems, the underdamped case where there are oscillations before the system settles down to its steady state value. We also, so in this plot here, even though the reference value is one, the system doesn't go to one, it goes to some value lesser than one. And we defined based on this, the term called the steady state error. And we also discussed in the previous week's lectures of how a type of a system decides its response, or in particular the steady state error with respect to certain input signals. This could be pure step signals, impulse, ramp, parabola, and so on. Hello and welcome to this lecture number 1 of week 5 on control engineering. I am Ramkrishna from Electrical Department, IIT Madras. In this, we will continue to build up on our discussions and, in particular, analyze the role of feedback in control systems. We will look at, in particular, three topics while we discuss today's contents. Of course, we did extensively talk about stability. We'll talk about tracking, we'll talk about regulation, and something called sensitivity. Of course, everything we will look in the context of LTI systems, where both the plant to be controlled and the controller are LTI systems. There will be certain objectives that the controller needs to achieve, and we need to design controllers to achieve those objectives. So two of the fundamental structures realizing these controls are the open loop and the closed loop. So before we begin, let's analyze the plots that we had earlier and see first what happens in case of a open loop system. I'll still use the same transfer functions which I had in an earlier lecture. So I have a plant of the form 1 over s plus 2. I'll call this G. I'll call this GC. We may also use notations of P and C as some texts would use. There will be a certain reference which the plant has to track and a certain output. Okay, let's say I start by asking myself a question. If y of s equal to 1, or I need y of s equal to, okay, now say 1 over s, or y of t should go to 1. Again, I'm talking here mostly in the steady state context. Okay, so what should be the reference for y of s to be 1 over s, or equivalently in the time domain y of s to be 1? Again, all in the steady state. Okay, so I just do simple math. So I have y of s over r of s is 5 over s plus 2. My reference, so y at steady state in s will be equal to limit s going to 0, s times 5 over s plus 2 times r of s. Okay, so I do all this math and I get that r of s must be equal to 2 over 5 s, or r of t must be equal to 2 over 5, or 0.4 for the output to be 1. I can also verify if this is correct or not. So what is, let's say, what is y of s when r of s is when r of s is 0.4 over s, The plant plus the controller is 5 over s plus 2. So this will be 2 over s plus 2. So I apply the final value theorem. Y at steady state is limit s going to 0, s times 2 over s plus 2, and this becomes 1. Okay, so if this is 0.4, this is 1. Okay, so this is fine. Of course, if I can look at in terms of an error, this leads to me an error of magnitude 0.6. Okay, so things will get worse when I say, okay, I still use the same plant, 1 over s plus 2. I add a disturbance, d of t. So this also may be a step. I have my usual controller, which is just a proportional controller. And then I have a certain reference. I'll just put this as 0.4 now. And y desired was supposed to be 1 again in the steady state. Okay, now what is the effect of this disturbance? Okay, look at it carefully. If I look at what is the effect of disturbance, so I just look at what is the y total output. Total output is both because of R and D. This will be y because of R plus y because of D. So this is what we compute by superposition. Okay, so I know what is y because of R just derived over here. My transfer function from y to d, sorry, d to y will just be along this path. So y of s over d of s will simply be 1 over s plus 2. Now, if d of s is a unit step, then y of s is 1 over s plus 2. And y in the steady state now becomes, I just apply the final value theorem, 0.5. So the total output y in the steady state is the y because of the reference plus the y because of the disturbance. It is now 1.5. So what has this disturbance done is to add 0.5 to the output. Not very desirable, right? So this is one thing we can see about open loop. What else can we see? Suppose now I have a plant of the form 1 over s square minus 1. Say there is, for example, possibly a disturbance, and I need to design a controller. So what is the nature of the plant? P, okay, I'll call it G or P, whatever, both are the same. S square minus 1. So where are the poles of the plant? Poles of the plant, I just equate the denominators to be 0. I get S equal to plus or minus 1. Okay. So this plant I can also write now as 1 over S minus 1, S plus 1, possibly a disturbance, or let's even ignore the disturbance now for a while. Okay, I will have, I can say, well, the C, why should it just be a constant? C can also be a system, which can say be of the form S minus 1, S plus 2, a certain reference, and a certain output. So this plant by itself is unstable. Now I say if I add a controller, if I just now what is this GC times G will now become 1 over S plus 1, S plus 2. Now this is stable because the poles are at minus 1 and minus 2. Okay, now the question we will ask is, can I do this all the time? Okay, so let me add a disturbance Okay, so again, what is now my y s by ds? Y s by ds is still 1 over s square minus 1. So this is still unstable even though I cancel the unstable pole of the plant with a controller. Okay, even assume there is no disturbance. I should accurately know this number one. I mean, what if certain changes in atmospheric conditions or any parameter changes this plus one or s minus one to say some other value or this to some other value. So will there be, even if I do s minus 0.00001 over s minus, I don't know, whatever, some okay, it should be close to 1, right? So let me say this is s minus, it just becomes 0.9999, and on the denominator becomes 1 plus 1.0001. So this will still lead to unstable, right? So there is this will not lead to any cancellation. Okay, so let's list down what have we learned so far. In open loop control, there is no closed signal path from the output to the control effort. The controller transfer function modifies this. This is the controller transfer function GCS. It modifies the reference input before it is applied to the plant. Now, as we saw in the previous example, the controller might cancel the unwanted dynamics. The controller actually canceled the the unstable pole, which was unwanted. The controller canceled the unwanted dynamics of the plant and replaced it with a more stable alternative, which was 1 over s plus 1, s plus 2. This became my G times GC after the pole zero cancellation. And you can see this in many practical applications as listed here. Okay, so just to formalize what we had written down, what we had obviously seen was open loop systems are heavily prone to disturbances, right? So in case number one, we saw that the output, which was 1, now increased to 1.5 in presence of a disturbance input. In the second case, even though I managed to cancel out the unstable pole of the plant with a 0 in the controller, the output or the disturbance made the system to be unstable. Okay, and output is also in general largely affected by the system parameters. Like electronic circuits are affected due to system parameters. Resistance can change with respect to temperature, and there could be external disturbances also in terms of sudden change in the supply voltage and so on. Okay, so what we saw in first was the total output was equal to, I just again take the same configuration here. The total output y of s is equal to the output because of r of s. So that was uh, r times g times gc plus d times gs. This is because output because of the reference, output because of the disturbance. Okay, so the total I can in that I can write it something like this. So the error or the difference between the reference input and the system output is given now by the reference minus the output for the open loop. So when I say I will use this subscript OL for open loop. Okay, and I have a large error, and the error also the disturbance also contributes a lot to the error here, as we had seen in our earlier case. Okay, so that brings us to the topics of discussion. We said we will look at, of course, we did a lot of analysis on stability. We know what stability means and how to infer stability. We look at the other two topics, namely tracking and regulation. So consider a thermal control system where the transfer function from the heater to the output temperature is given. So this is the model of the plant, a second order system. The goal is to design a controller. Let's see how the plot first looks like. The goal is to design a controller. See, what is my reference here? Reference is no longer a point. Reference is no longer a 24 degrees or a 60 kilometers per hour speed. The reference is such that it is a line passing through the origin with a certain slope for about 30 seconds, and after 30 seconds it just becomes constant. So the objective here is to make the systems follow a time varying reference signal. It's not a constant signal. So what does the system what should the system do, or the controller must minimize the tracking error while adapting to changes in the reference. You see, at this point the reference changes. Okay, so just look at the plot. So I start with this blue curve is my actual output. So because of the dynamics, the error starts from zero. It again the blue and the red line cross each other. The system responds slowly. It crosses this reference here, and then experiences a change in the reference value here, and slowly goes to adjust itself towards the new reference value. And of course, you see the error pattern, right? So at this point, the error again goes to zero, then it increases, and somewhere here my reference changes. The reference now just becomes a standard regulation problem where I just want to track a number. Okay, so to summarize, the goal here was to design a controller to track the reference temperature. So initially it's a ramp of 30 degrees Celsius per second for a duration of 30 seconds, and then a steady state value of 300 degrees Celsius. So the idea is to excite the system with an input of size zero point 0.3. Since the DC gain of the system this is a DC gain. DC gain essentially would mean the gain of the system when S equal to 0, so that the steady state is 300 degrees. You can work these details out. This is the same as the other example that we worked out. What should be the R such that Y should be 1, and it turned out to be 0.4. So please check these calculations. They follow the same process as different. So this is about any kind of a tracking problem. Okay, then the standard problems that we will do is about regulation. What is regulation? Regulation refers to the ability of the system to maintain a constant output value. Could be a temperature of 24 degrees, a speed of 60 kilometers per hour, and so on, despite external disturbances. And the problem of regulation, therefore, is to keep the error small when the reference is a constant set point, and there might be some disturbances. We will see those things also. In open loop system, the controller has no influence on the system response to either of the disturbances. Okay, so open loop is not suitable for regulation, because what we see is the transfer function from the disturbance to output doesn't really uh, the controller doesn't really have any say on that. It just goes directly from here and here, and therefore we saw how even though smartly the controller was able to cancel the unstable pole, the disturbance bypassed that particular cleverness of the control design and directly affected the output. So what we can see or kind of easily infer is that the controller has no influence on the system response to disturbances, so on with the noise also. So open loop system is in general not suitable for regulation. When I say regulation, is not just to maintain things at a constant desired value, but also look at its ability to reject disturbances. Okay, so if we and what we saw earlier also was about what happens when we introduce a step disturbance. So we'll see what happens in this tracking problem. So if we introduce a step disturbance at the steady state, the system has reached a steady state, and then I'm saying, okay, let's see what is happening with the disturbance. The output with the open loop proportional control, it will not be able to attenuate the disturbances. So that's we saw how the output changed from 1 to 1.5. I'll just see quickly also here, right? So here the system kind of reaches steady state value. Then there is a disturbance here, and you see the error increases with disturbance. And then, so this is my reference output. This is how the tracking problem worked to get the system to this number 300. After there is a step disturbance, the system doesn't settle to 300, but it goes to a new value of 350. Okay, so I see that there is nothing that the controller can do to nullify the effect of this disturbance. Okay, so stability, of course, we know that stability must mean that stability means that the poles of the system must be in the left half plane. In the open loop case, these are the poles of G times GC. So now this is exactly what we had said, right? Even if A of S has a pole in the right half plane, so we had A of S was what? So we had S minus 1 over S plus 1. Even if AS has a pole on the right half S plane, one idea could be to design C of S such that it cancels out. Exactly what we had seen in that example. And however, what we also saw was the unstable pole remains, and slightest noise or disturbance will cause the output to grow unbounded. Okay, it can make the system unstable. Okay. Similarly, if the plant also shows a poor response because of the zero of BS in the right half plane, attempt to fix this by cancellation of a root will similarly result in an unstable system. So suppose there is something unwanted, uh, some not very good things happen because of this BS or the zero in the right half plane. We just cannot do it by using cancellation of a pole, vice versa, what we did earlier. It will still result in an unstable system. Okay, so what do we do with all this? Okay, so we'll just formalize things and all those examples that we had done. So suppose a plant is designed now with a gain G at a particular frequency, but it changes to some G plus delta G. It could be changes in parameters and so on. And I can see what is a fraction or the percentage change of gain is delta G by G, or you can also measure in percentage. Let me call the open loop gain as L equal to G times GC. Many texts would also do this as L equal to P times C, like the the transfer function of the plant times the plant transfer function of the controller. Okay, so in this case, we'll see what happens to when G or when G changes from G to delta G, what happens to L? L changes from L to delta L. And what is the change? My L was G times GC. Now my G changed from G to delta G and with a GC. Okay, so this will cause a change delta S as I think this should be okay. So this will just work this out, right? What is L plus delta L is G times GC plus delta G times GC. So delta L would be delta G times GC. So this should be the reverse here. Okay, so we now define a new notion that the sensitivity S of a transfer function L to a plant G. So how does how does changes in G, the plant, affect the loop here, the plant times the controller, right? So I define this as the change in the total loop transfer function delta L by L to delta G by G. So this gives me this number G over L, delta L over delta G. And this kind of gives us a little quantification of how changes in plant result to changes in the overall loop. Okay, now this is good. Let us come to the closed loop architecture. Okay, so we'll go back to our plots that we had seen here. There were instances where, let's see what is happening with the presence of disturbances. So in this yellow line, the effect of the disturbance is such that it causes the output because of the disturbance to settle at some small value, should be like zero point 0.1 something. Similarly, on the right, we have a system where the effect of a step disturbance causes an additional value of zero point 0.2 in the output. Okay, let's go to the next page. So there is disturbance here, but in the steady state, the effect of disturbance goes to zero. Okay, how can all these things happen? Okay, we'll again look at example of this form. And let's say for simplicity, I say I have 1 over s plus 2 as my plant. Say a step disturbance 1 over s. The controller is 5. Let's say I have y of t as my reference, sorry, as my output, r of t as reference, and let me say I can choose the reference to be 1, and see what happens to the output because of this reference. Okay, so in one of the earlier lectures we had seen what is y of t in the steady state when r of t was 1 or 1t. Now we'll see what is the effect of disturbance on the output. So what is y of t due to d of t? So again, I look at the transfer function y of s over d of s. This will no longer be just this one because of this closed loop. You can work out the math to say that this will be g over 1 plus g times gc, where this is my plant, this is my controller. Okay, let's do the math here. So G is 1 over S plus 2. GC is 1, sorry, 1 over S plus 2 is G. 1 over 1 plus GC would be, my G is 1 over S plus 2 with a 5 in the numerator. So this will be 1 over S plus 7. Okay, now if D of S equal to 1 over S, then Y at steady state due to disturbance will be limit S going to 0, S times 1 over S plus 7, 1 over S. This is 1 over 7, or I think it will be 0.14 something. And I go back to the plot, the earlier one, this exactly is 0.14. Is the additional output that is added to the system because of the disturbance. Okay, now let me do something else, because we had looked at the type of the system and we saw how different types of system responded to different input or different reference signals. Okay, so I just still take the same example uh, and say I have a so by the way, this system by itself could not track a reference, right? This is when G was 1 over S plus 2, GC was equal to 5. The output was somewhere like zero point 0.7 or something, or zero point 0.7 or zero point 0.8, somewhere here. We had computed this. So this is, I look at it as a type 0 system. And for it will have some finite Kp resulting in some steady state error. So a type 0 system will track a step with some error, and that is exactly precisely this error. Okay, now let's see what happens to a type 1 system and what happens to a type 1 system when there is disturbance. Okay, I still take the same system, but I make it type 1. So instead of just s plus 2, I have 1 over s plus 2. In this, I am only interested at the moment in the disturbance. I'll have a 5 here. I still call this reference as 1, and I have an output y, and I have a d. Okay, and let's see what happens to the disturbance, or what happens to the output because of the disturbance. So now here y of s over d of s. Again, I can safely assume r equal to 0 largely because I'm working with superposition here because everything is a linear system. It's like in b g over 1 plus g times gc. We do the math. This is 1 over s plus 2 over 1 over 5 in the numerator, which is the controller s plus 2. Okay, so this will be 1 over s square plus 2s plus 5. Okay, so the y steady state, if the disturbance d of s is equal to 1 of s, this will be limit s going to 0, s times the whole transfer function and the input. So I do all the math, I get a number of 1 over 5. Okay, let's go back to the plots. So what is 1 over 5 is 0.2. And okay, so something we see is something very similar here, right? This is 0.2. So what we saw is that the system was type 1. The type 1 system tracks a step. So therefore the error is 0 because of the reference, or because it's a type 1 system. But I see some error, or I see some contribution of the disturbance to the output, which is not desirable. What I want is, if there is a disturbance, the system should reject it at steady state. There might be some initial transients, but I should be able to make the effect of disturbance on the output to be equal to 0. Okay, so let's see if there is something I can do about this. Okay, so I'll still play around with the same structure. I have s plus 2. I have a d. I still want the system to be type 1. So I put a s in the denominator inside the controller. I have a r of t and this one. So I have a y of t. So I still do same. What is the effect of disturbance on the output? I just calculate the disturbance, the transfer function from the disturbance to the output. This will again be g over 1 plus g times gc. G is 1 over s plus 2. 1 plus g is 1 over s plus 2. 5 over s. So this will become 2. So the denominator I will have s square plus 2s plus 5. The numerator will have a s. Okay, so y at steady state, because of this disturbance, again choose d of s to be equal to 1 over s, a unit step disturbance. You can choose anything and just do the analysis, doesn't matter much. So this will be limit s going to 0, s times this transfer function, s over s square plus 2s plus 5, 1 over s, these go away, this s remains in the numerator, this becomes 0. Okay, so go to the next plot. What we see here is that the effect of disturbance becomes 0. So this is also a type 1 system, but we had, instead of a s in the denominator in the plant, we had a s in the denominator in the controller. So this we will also see soon, that this will be called as the integral control action. Okay, whereas if I just have a number here, this will be called proportional control. Okay, we'll come to that a little later. For now, what we see is that in some cases, which I will kind of generalize, there is the effect of disturbance is nicely nullified. That in the steady state, the transfer function from or the effect, the y because of d just goes to 0. So a typical closed loop architecture now, I will have, of course, the plant, the controller, I'll have a feedback loop, possibly there'll be some noise here, some disturbances, and this architecture. So this feedback control uses a sensor to measure the output, right? So there's somebody who will measure the output, and the feedback indirectly modifies the dynamics of the system. So it will just check if my reference is equal to the output. If there is a difference, the controller will pump in equivalent amount of energy to make the plant go to the desired value. So total output of the system now is because of the total output because of the reference. And this term here will be the transfer function from R to Y. This will be a transfer function from D to Y, and this will be a transfer function from N to Y. N is the noise signal, and we see the minus sign here is because of the negative feedback term. Okay, so the control input U of S, which is, oops, sorry, the control input U of S, which is seen to be here, can be computed to be now in this way. So this U of S comes from uh, GC times the error. So U is GC times the error signal. This we have defined. And this error is coming from the reference minus the signal here, which is H times the Y. And this Y comes from here. So we can just do the quick math and easily check that the control input is given by this number. Okay, we were interested in error, right? What is the error because of what is the error because of the type of the system? What is how to make this error zero? And we had a beautiful relation between the type of the systems and what kind of signals they can track. So the tracking error now is the error because of the reference, the error caused due to the disturbance, and error caused due to the noise. There will be an error caused because of the disturbance, because we saw at least in couple of cases or more or three cases that the disturbance contributes a positive number to the output. Just like this temperature here. There's no disturbance. My temperature was nicely at 300. There is disturbance. The temperature increases from 300 to 350. We had seen in I think week 2 lecture, we were talking of signals where disturbances on a car in terms of maybe doubling its weight reduced its speed from say 60 to 40. So there is some effect of disturbance on the error. Okay, so let's analyze each of these things and the contribution of each of these things. Okay, so we have done so far where things that there was no disturbance and there was no noise. The error took a very nice term like this, 1 over 1 plus G times GC times RC. So we also call this as now 1 over 1 plus L times R of S. Or in other words, the error was related to the reference by just 1 over 1 plus L. And if I just look at the magnitude of the error, I would want this magnitude to be very small. And for this magnitude to be very small, the L must be large. Okay, so we'll see that in a bit. So, but we are interested now also in what happens when G changes from G to delta G. And does the closed loop behave slightly better than the open loop when G changes from G to delta G? So the error will change from E to delta E. And so this is a total error because of the G changing from G to delta G. The delta of E I can now compute quite nicely to be something. I just leave this math for you to do. So delta E takes this form now, assuming that the variations are very small. So that G times GC will be much larger than delta G times G of S. So therefore some of these terms here will become unimportant. And we do all the math here, and if L of S is very large, So just like I said, so the error is 1 over 1 plus L. We want this to be very small, and therefore for this to be small, the L should be very large. For large L, I just have delta of E now has a very nice inverse relationship with the L. Okay. Now, the first observation here is that the larger value of LS results in smaller changes in the tracking error. So G changes from G to delta G. If L is large enough, then the effect of delta G on the error can be made as small as possible. Okay, so let's do a bit of an example here. Again, I guess go back to the thermal control example, where the goal is to design everything as similar. With initially, I'm tracking a slope of 30 degrees per second, and then I'm going to 300. The control strategy is to minimize, is to design a controller that minimizes the error between the reference signal and the output, and also I want a smaller steady state error. So let's say I choose a controller of this form. Okay, so we just saw of how adding a denominator in the controller had good effect on disturbances, but we'll do that much more detail in the next lecture. So when I do this, okay, something nice happens that compared to the open loop, the closed loop has a very small tracking error. Okay, the closed loop was not behaving very well. The open loop wasn't behaving very well in example like this. And we also saw the other smaller examples where we could actually compute these values. Okay, so now I'm kind of good to define something. So the closed loop output, because of the reference, the disturbance, and the noise, takes this form. Again, I can just add this up easily because of superposition. I'll keep on repeating this until we kind of know this by heart. Okay, so the closed loop steady state gain or steady state transfer function. So LCL will be just this. This is the closed loop transfer function. I'll call this as LCL. And okay, what happens to the closed loop transfer function due to a change in delta G? Okay, so I just instead of G, I'll now have a G plus delta G. I do all the math and I get a number which now looks like this. That the change in the closed loop transfer function because of change in delta G is now just dL by dG over delta G. Okay, so the general expression now for sensitivity, again, we'll just also remember what we did in the open loop case. So this was changes. Okay, a little back. I may have to go. Just the sensitivity is here. Yeah, changes to the overall transfer function to the changes in the plant transfer. In the open loop, the overall transfer function was just GC times G. In the closed loop, the overall transfer function is not just GC by G, but because of the feedback, it becomes GC over 1 plus GC. So if I still look at it as the ratio of the change or DLCL by DL over DG. Okay, so let me just see the notations carefully. The change, okay, oops, sorry. You can write this as delta LCL by L over delta G by G. And some people also call this as T. Okay, so I do all the math, I do this little differentiation here. What I get is the sensitivity of the closed loop transfer function with respect to changes in G is also 1 over G times GC. This is also equal to 1 over 1 over L. L was the loop transfer function which we saw in the earlier. So the sensitivity of a transfer function also has directly to do with error. And therefore, which I would really want to keep this as small as possible so that the system is less sensitive to changes in error. So the error signal which was sitting over here in my closed loop, this also has something to do with the sensitivity. It is directly related to the sensitivity. Okay, so for the open loop, it was much different, but in the feedback, the error in the overall transfer function gain is less sensitive to variations in the plant gain. So, and by a good factor, by a factor of 1 over 1 plus L compared to the open loop. So, definitely we could see here that the open loop system is much more sensitive to variations than the closed loop. Okay, so stability. For the closed loop system, I'm essentially looking at, because I have G times GC over 1 plus G times GC, I will look at the denominator, and this will be also called as the characteristic equation. Okay, and if if G is a polynomial of this form, GC is a polynomial of this form, I am interested in solutions to this polynomial to check whether the system is stable or not. Okay, feedback also gives me more freedom to the controller design than in the open loop case. Open loop case was very restrictive. Here I can choose my C and the D. As I've seen in some earlier example, I had 5 as a controller. It did few things for me. 5 over S did me really wonders in terms of rejecting the disturbances and so on. Okay. So, and unlike the open loop case, having a pole of AS in the RSP does not prevent the design of a feedback controller. Okay, so I start again with the same example. G of S is 1 over S square minus 1. I have, which means that B of S equal to 1, A of S equal to, is something like this. And say I just look at the GC of this form where I can choose my gamma and delta to make the system stable. Okay, so let me take gamma equal to 1 so that the characteristic equation can now be written in this form. And I can really solve the second order equation to say maybe that the closed loop poles can be at say -4 and -4, where the open loop poles were at +/-1 and so on. Okay, we'll discuss a little more on this a little later. So the idea of this is to just say that having a feedback, of course, it rejects, it makes my steady state errors smaller or sometimes even zero. It rejects disturbances, but it also gives me a lot of freedom to design my control laws. Okay, more about disturbance rejection. So I'm now interested only in what is the effect of disturbance on the error. Okay, so this will be simply G over 1 plus L times ds. So if G is fixed, then increase in the loop gain can cause the effect of the disturbance to decrease. Okay, and again, the thing here is this is with this 1 over 1 plus L. And disturbances are typically at low frequency. If you see some step signals, maybe my set point can go, or not set point, but disturbance can maybe go up or a little down. But these are not really kind of fast moving things. So for the purpose of disturbance rejection, I can increase this L, which is, I'll call this as the loop gain at low frequencies. We'll see this when we exactly do design of systems. For now, just look at it. So what kind of signals come across as disturbance signals? These are low frequency signals. So if I just do make L large at low frequencies, that kind of solves my purpose. So this is equivalent to increasing the controller gain at low frequency because I'm considering that my G is fixed. That is, only decrease the sensitivity of the closed loop feedback system only at low frequencies. Why will I not do it for all frequencies? Okay, let's look at the effect of noise. I just put D and R equal to 0. The effect of noise now looks something different. It has L in the numerator over 1 plus L. So this will also be known. So this the name for this 1 over L plus 1 over 1 plus L is the sensitivity function, and L over 1 plus L, we will call this as the complementary sensitivity function. Okay. Now, a small loop gain leads to a good noise attenuation. Okay. And noise is typically introduced at high frequencies. So, for the purpose of noise attenuation, the loop gain is tuned to low values at high frequencies. If it's like really small, then I can nullify the effect of disturbances, because this number by itself goes very small. Okay, so therefore the controller gain is decreased at high frequencies for noise attenuation and increased at low frequencies for disturbance rejection. Okay, so to summarize, we have seen what is the effect, or what's the comparison between open loop and closed loop. Advantages of feedback is that it improves the stability of the system, decreases sensitivity with respect to system parameters where G was going from G to G plus delta G. It helped in rejection of disturbances, reduction in steady state error, as we had seen in previous lectures, and improved accuracy by, of course, by measurement attenuation, which comes from the complementary sensitivity function T equal to L over 1 plus L, and of course increased bandwidth. Disadvantage could be the reduced gain in the overall system, because overall system earlier had a gain of L, which was G times GC. Now I will have overall gain of L over 1 plus L. And of course, increased cost and complexity, because you have to spend time, effort, and money in building those systems, buying sensors, appropriate sensors, maybe filtering out the noise, and so on. Okay, so we did a good amount of analysis on open loop versus closed loop, tracking errors, disturbance rejections, noise attenuation, which part of the controller is how the controller should be designed to have high gains or low gains at different frequencies, and so on. And slowly, with this motivation, we will learn to design controllers. That is coming up in the next lecture. Thanks for listening.